understanding what you're reading and able to think about it and write about it fairly well. So that should be kind of what we expect out of you as juniors and seniors. Um, Avery, since you are here, do you and Mason need to talk to me between now and Monday? Or are you just
I
gonna
don't know. That's a good question.
wing it? I think Mason's not feeling well today, according to Elizabeth.
I'm probably just gonna meet up with him this weekend.
Okay, all right.
Um, do you want us to like just do it together kind of thing, or did you want like him
He
to do
has
his?
he has one paper and you have the other.
Okay. So like, did you want it like separately within the class then? Like he goes over his paper, I go over my his again.
I would think so, but with the assumption that the topics are related.
Yeah.
So if you guys want to do things like splitting the introduction or something like that, I would be okay with that. But I really want him to cover the Brody 1993 paper and for you to cover the Brody and Jensen 95 paper.
Yeah.
Hopefully, um, I'm going to sneeze. I'm going to sneeze. I'm not going to sneeze. Okay, fine. Hopefully, conceptually, this is a little easier of a paper to handle than the last one. Um, but we'll see. We'll see how you guys do. Let's see. Questions about anything course related or predator prey related? All right. So we were about to get started on the not the cute case study, the cuckoo case study. This is a situation where once again we might have a predator-prey arms race, but in this case, it's not really a predator-prey arms race, it's a parasite-host arms race. And the interesting thing about parasites and hosts is that you can use the same mathematical models to describe predators and prey. You can use those to also describe hosts and parasites, as it turns out. And so the evolutionary dynamics of predator-prey interactions are very similar to the evolutionary dynamics of parasite-host interactions. So in this case, cuckoos, the European cuckoo, um, do a bunch of fairly complicated sorts of behaviors. For example, they steal all of the erasers in the room. Oh, there's one. No, they don't steal erasers. So what the cuckoo does is it flies into a nest. Let's imagine that the nest has 4 eggs in it, and these 4 eggs are laid by the host bird species. And what the cuckoo then does is it basically removes one of the host eggs and lays one of its eggs in its place. The host bird comes back. In this case, the host bird is blue. The host bird comes back and will incubate those eggs if it doesn't recognize that this is a cuckoo egg, not a host egg. As it incubates those eggs, the cuckoo egg, which is generally larger, so I could actually draw that larger, it oftentimes will hatch earlier. And upon hatching, the baby cuckoo chick will actually boot all of the remaining eggs out of the nest. So now there's just a baby cuckoo in the nest being fed by the host bird species. The baby cuckoo doesn't look anything like a baby of the host bird species, but once again, there's kind of this biological imperative to feed the baby, because if you don't feed the baby dies. And so, if you are an indiscriminate host, and you get parasitized, your fitness plummets to 0 with this particular clutch because you're now raising a cuckoo chick, and the cuckoo chick and the cuckoo parent have kicked out all of the eggs from your nest. So this is what happens if you're parasitized. Your fitness goes to 0. If you're non-parasitized, no big deal, because you have 4 eggs in your nest, and you raise these 4 babies. And so in theory, your fitness is 4 if you're not parasitized. So if you live in a place where there are a lot of cuckoos that might parasitize you, then you might expect natural selection to favor individuals that are capable of discriminating cuckoo eggs. So you might also see natural selection in places where there are lots of cuckoos, which is called a brood parasite, a parasite that parasitizes the brood, the babies. You might also see selection favoring individuals that create distinctive eggs that make discrimination easier. So when you look at these eggs here, you can see that these eggs are very descriptive, but here you have a situation where this egg doesn't really look like any of the other of these eggs. Um, these are actual eggs from birds that are the host birds. What? Da, 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 da. Oh no, sorry. This is the cuckoo eggs, and these are the host species eggs. And you can see that in many cases, the cuckoo egg matches the host species egg, except for this situation here, where there's serious mismatch. And so this is, from top to bottom, this is the robin, the pied wagtail, and the dunnock. So in the dunnock, we have poor match. Where this produces kind of a blue egg, and the cuckoo produces this mottled egg. In all the other cases, the cuckoo egg is pretty well matched to the host species. The reason for that is that if this is happening to the host species because selection is acting on the host species to make them better at discriminating cuckoo eggs, and part of that is by creating distinctive eggs that makes discrimination easier, what's happening in terms of selection on the cuckoo itself? Cuckoos are exerting selection on hosts. This is the evolutionary response to that selection. What would then be the evolutionary response to selection by hosts on the cuckoos? What's that? Yeah. So you would expect the evolution of mimetic eggs. And that's what you see, generally speaking. So what do you think is going on with this pair here? The cuckoo and the dunnock. What do you mean further along? It doesn't match. So what does that tell you either about the dunnock or the cuckoo?
mean, like, they can copy them, but then their eggs don't match anything else.
Okay, but these are geographic races, so you find these are all produced by cuckoos in different parts of the cuckoo range. So when it talks here about genetically different host races, so they're matched to the species. So this bird is laying its eggs consistently in the Dunnock's nest. What is it that causes the distinctiveness of the host eggs? The coloration and also the size a little bit, although this is pretty matched size. The modeling is different. This modeling is different from this modeling, is different from this modeling, is different from this modeling. So the host bird species are making their eggs distinctive by changing the color, but not just changing the general ground color, they're also changing the pattern and size and shape and everything of this modeling. And when I say they're changing, what's happening is that patterning is evolving. Because a female doesn't sit there, she's about to pop out an egg and she thinks to herself, oh, how am I going to color this egg today? She's not doing that. This is an evolutionary trait that is evolving over time. And these species have all evolved this modeled patterning that is distinctive so that the female presumably looks at her egg and says, ah, that's my egg. So what are Dunnocks probably not doing? Dunnocks probably are terrible at either distinguishing eggs that don't look like theirs, or if they do distinguish that, they don't do anything about it. And they probably don't do anything about it actually because they just don't have the evolved response of recognizing eggs that aren't their own. And so in this case, we might expect, in this case, for Dunnocks to not discriminate. Why do they not discriminate among the eggs? Well, they just don't discriminate among the eggs. We think that that's the case because they're not creating distinctive eggs. If they were discriminating against cuckoo eggs, what would you expect this egg to look like? It would look more like this one, wouldn't it? And so you must have a case where there's no selection on the cuckoo to match the egg of the Dunnock. As a result, the cuckoo egg in that particular race is not evolving an altered egg structure. So it turns out that, oh, here are some pictures of cuckoos. This is a female cuckoo coming in, getting rid of a host egg, just dumping it over the side of the nest. She's in the host bird's nest. She lays her own egg, and I forget which one of these is her own egg. Then that egg hatches out earlier, and when the baby cuckoo hatches out, the baby cuckoo will take its little wings, its little fledgling wings with no feathers on it, and it'll put its butt towards the edge of the nest, wiggle the egg up onto its back, and then just tip the egg out of the nest, clearing out all of the host species eggs, and then you have the nest all to yourself, which means you also have all of the parental care of the host parent all to yourself. Something on my keyboard. Researchers, way more clever than probably any of us in this room, including myself, have figured out ways of measuring color on eggs. And so you can take measurements of the wavelengths reflecting off of the eggs. And in some cases, the wavelengths are going to be reflecting off of the ground color. In other cases, the wavelengths are going to be reflecting off of these distinctive spots, this distinctive modeling that is found on the eggs. And they can basically measure the color pattern of cuckoo eggs and host eggs. And I forget which is which. Red. Oh yeah, so the cuckoo is red and the host is blue. And you can see that in some cases the overlap in terms of how well does the cuckoo's color pattern overlap the host pattern is relatively tight with a lot of overlap. But in some cases it's less so, like with the meadow pipit and the reed warbler. But look at it in the dunnock. In the dunnock, there is no overlap between those two eggs. A cuckoo egg doesn't look anything like a dunnock egg. And then what you see on this chart right here is you see a bunch of these species where it plots on the x-axis the rate at which cuckoo eggs get rejected from the nest and the percentage of overlap. And what's interesting here is the greater reed warbler has a really high rejection rate and a decent amount of overlap. The brambling has once again a pretty high rejection rate and a pretty high overlap. It would be nice to see the redback shrike, but it's not on this list here because that's a species that rejects eggs, cuckoo eggs a lot, and has a really, really high overlap between the cuckoo egg and the shrike egg. Where's the dunnock on this? It's a 0 and 0, isn't it? The dunnock hardly ever rejects cuckoo eggs. As a result, cuckoo eggs don't have to look anything like dunnock eggs. There is no selection on the cuckoo egg morphology because the dunnock doesn't ever reject them. As the rejection rate goes up, selection has acted on cuckoos to produce eggs that overlap the color pattern of the host. One of the things that you might have thought when you were thinking about this as you were reading your book, hopefully, is that if selection by the cuckoo is increasing the distinctiveness of the eggs and the discriminating ability of the parents, you might actually expect the rejection rate to be highest where the overlap is lowest, right? Individuals that are being parasitized by cuckoos who are not doing a very good job of matching the eggs of the host, you might expect that rejection rate to be really high because the bird comes back, looks at the egg, sees, oh, one of these eggs is not like the others, it's been watching Sesame Street, and then boots it out of the nest. But that's actually not what we find. We actually find that there's this close correlation between the complexity of the egg and the ability of the host species to recognize the egg and reject it is correlated with the match of the cuckoo, and that is exactly what you would predict if this was an evolving arms race. Selection